Hello everyone. In this video, I will demonstrate the framework I developed for the full characterization and efficient optimization of water and energy systems. So this is the main screen of the framework, and we have the properties panel on the left-hand side, and we have the working area on the right-hand side. And the working area have 5 different screens that we will go through one by one in this demo. So let's start by putting the screens next to each other. And starting by the properties panel on the left-hand side, as you can see, the framework can import the data from either a local directory or from an SQL server. But for the sake of this example, let's use a local data source. So we browse our data file and we import the data. And we can see that the framework shows us the progress of importing the data in the progress bar and in the message text box. And we also see that it detects all the parameters it found in the source data file. So the next thing we need to do is to select the parameter that we want to model and optimize, or in other terms, the objective parameter. And for the sake of this example, let's select the energy consumption. And we have this many of data points in the source data file and this many of parameters. Now we can start by modeling all the parameters we have in hand. And we can do this in the parametric characterization window. So as we can see, we have different correlation models. These models use the covariance between the data points we have to detect any linear correlation between the parameters we have. So let's select this correlation model and let's select this heat map. Now, when we click test, we see that the framework will generate a correlation matrix between all the parameters we have. For the sake of this example, if we look at the energy consumption, we see how the energy consumption is highly correlated with the airflow rate. We see also that the energy consumption have a low negative correlation with the salinity. Another example, we see that the cyclone pressure drop have a high correlation with the airflow rate. The next mode we will see now is the multivariate distribution mode. In this mode, we can develop a probabilistic model and train it to predict the system performance as well as obtain the covariance matrix. And we see here that the objective parameter we selected is already here. Then let's set up the properties of our model. So let's select the rational quadratic kernel, and we can select either a standard, additive, or product structure. So let's make it a product structure kernel to be more efficient. And let's select the dimension of this product structure to be 50. And we will use 20% of our data set to test our model. So we will use 80% for the training of the model and 20% to test the model and make sure it's not overfit. Then let's use 15 iterations to train the model with a learning grade of 0.15. We can either shuffle or scale the data, but for the sake of this example, let's just scale the data between 1 and 5 to avoid any mathematical overflows. The last text box we see here is for parallel processing when we have multiple machines, but let's avoid it for the sake of this example. And then we can start the training process. And we will see how the framework will show the progress of the training process in the training log and in the progress bar down there. And then I will skip the next couple of minutes in this video until the end of the training process. Now that the model finished training, we can see all the errors associated with the model training and tested here in the error table. So we see different types of errors for the errors associated with the training data points and testing data points. Then we can show the results by clicking this button. So we have the model's predictions with the training dataset and the model's prediction with the testing dataset. We also have the all data points covariance matrix down here. So we have the covariance between each data point and all the other data points. And we can zoom into any data point we want. We can also view this window alongside with the data window to view the entire data set we used in this process. We can view the training data set and we can view the test data set. As for this selection panel down here, it will show us the data point we select in any one of these plots. So we can show all the conditions associated with any one of these predictions. Now that we finished training the model and testing it, we can save the model. We can load it anytime in the future. And we can also use it to predict any other set of data points of the same parameters. The last mode we will see now, and the most interesting one within the capabilities of this framework, is the ability to use Bayesian search methods to guide the technology development and minimize any number of testings required. Now, if we go to the mode of search method, here we can set up our Bayesian search method. So we can start by setting up our Gaussian process, and let's use the rational quadratic Gaussian process. And then we can change the hyperparameters of this model as we please. But for the sake of this example, let's stick with the default values. Then we can select our acquisition function. The acquisition function in general is an inexpensive probability function that is optimized at each iteration to select the next test data point. And for the sake of this example, we will use the maximum expected improvement. And we will set up our trade-off parameter to 4, and we will scale our data to a range between 1 and 5 to avoid any mathematical overflows. Now let's start by sampling one data point. And we see how the model starts by fitting the Gaussian process around this one data point we tested. And we see one more data points because of the initial conditions. And at each iteration, the model will find the maximum optima and the minimum optima. The next step, let's do 5 queries. Now we see how the model started to teaching the Gaussian process how to be fit around the performance map of the system we have. So we see in this region how it started by fitting these 5 different data points around the system. And we see how the uncertainties are minimum around the data points we sampled, because now we have knowledge of these regions. But we see how the uncertainties maximize around the regions that we don't have any prior knowledge of. The same applies around this data point. So we see how the uncertainties are minimum around these data points. The next stage, let's do 10 samples. And now we can see how the model is almost converged around the real system performance. We see how the Gaussian process is perfectly fit around the regions where we sample our data points. Now let's do 15 queries. And we see how the Gaussian process is almost fully converged around the real system performance. And we see that our model already detected the maxima and the minima of the system in this region. So we already detected the minima in this performance map and the maxima in this performance map. And it's pretty close to the absolute maximum. Now let's see what happens when we query 20 data points. Now the Gaussian process is almost 100 convert around our performance plot. So we have the energy consumption predicted by the Gaussian process trained by the Bayesian search method. They are almost fully converged around the real energy consumption. And in real life, we might not have prior knowledge of the real system performance. And that's why we apply our Bayesian search method to reach our optimum performance with minimal testing required, especially if we have an expensive large-scale technology. Making a lot of testing might be quite expensive, but using search methods will drive us to the optimal performance with minimal testing required. And we see how the model is quite confident around the data point it already have prior knowledge of, and we see the uncertainties maximize around the regions where we didn't have any prior testings, like these regions. And these regions. But the uncertainties are almost zero around the data points we have prior knowledge of. And at the end of the optimization stage, we will find a log of all the queried data points that we needed to reach the optimum performance and to fully characterize the system in the queried data points table down here. Finally, after finishing all our modeling and optimization efforts, we can show all our modeling and optimization results in the results window. So we can have all the information about the data set we imported, the errors in our predictions, the testing data sets in the X and Y, the training data sets, all the parameters we have, all the correlations between them, all the models and kernels we used, and all the other information we used throughout the modeling and optimization.